Quite often, in many applications, you need to deal with narrowband signals. For instance, communication systems, ultrasound, imaging, and lots of other applications. Anytime you try to transmit a waveform or receive a waveform, you have to transmit it in narrowband. Anytime a light or wave is traveling between two places in astronomy and so on, narrowband signals are involved. In this video, we want to examine under what condition a narrowband signal which has a form like that is either a strictly sensitive station or wide sensitive station. So this question is very important and we want to examine it in step by step. So if you want this random process to be wide sensitive stationary, mean of x of t shall be constant. So this is equal to, so in this example, A is called in phase component, which is a random variable. B is called quadrature component, which is another random variable. Omega is frequency. And in this example, we assume that it's not random. In that case, mean of x of t is equal to mean of A, which is random, cosine of omega t, and then plus mean of B, sine of omega t, because omega t are not random. So if you want these to be constant, so for all values of t, these should be constant. So for instance, if I put t equals 0, this quantity will become mean of A. Now you could put a value for omega t such that this is equal to pi over 2. If I do that, cosine of omega t becomes 0, and then plus this will become 1, and then I get mean of B. So therefore, because these should be constant, these two guys should be equal to each other. Alternatively, I could replace omega t by pi. In that case, cosine of omega t will become minus 1, so I get minus mean of A, and then sine of omega t becomes 0. So in that case, these three guys should be equal to each other. So mean of A should be equal to mean of minus A. Therefore, these should be equal to 0. Because this is 0, this shall be also 0. Now, if mean of A and mean of B are 0, these become 0, and these become 0, and this becomes 0. So it is necessary and sufficient for this random process to be stationary in the mean sense, only and only if mean of A and B are both equal to 0. Now, but this doesn't make it WSS because we need to also evaluate the autocorrelation function. So I summarize, mean of x of t is equal to that. We evaluate this function for 4 different values, and quickly you conclude that mean of A and B should be 0 for this random process to be stationary in the mean sense, or the mean is constant. For wide sensitive station, we must also have these guys shall be equal to only a function of 2. It shouldn't be a function of time t. So when I write that, so this has a cosine term and a sine term, and this one same thing. So when you multiply them, you get 4 terms, and then you calculate the mean. So if you multiply them 4 terms, the 4 terms are equal to that. 2 is missing here. And we want these not to be a function of time t. So in that case, we could evaluate this function for the same things. So the cosine is 1, sine is 0, and so on. And then quickly conclude that all these 4 values obtained for these 4 values of time t should be equal to each other. In that case, you could conclude that these terms shall be 0, and mean of A2 and mean of B2 also should be equal to each other. So the necessary and sufficient condition for this random process to be wide sensitive stationary process is this one, and this one. So if these 3 conditions are satisfied, a narrowband signal is WSS. This is necessary and sufficient condition. The next question is that the same random process, under what condition is necessarily or sufficiently is a strictly sensor station process? The answer to this question is also not very difficult, but is very important. So here we have to prove that this random process, we want to prove that this random process is a strictly sensor stationary only and only if, first of all, we know that if it is a strictly sensor stationary, always a strictly sensor stationary is the strongest sense of stationarity. It should be wide sensor stationary. So the conditions in the previous slide should be satisfied. But it is not necessarily nor sufficient for SSS because SSS. So we want to prove that it is strictly sensor stationary if the pair of random variables A and B has a circularly symmetrical distribution. So let us prove it, a necessary and sufficient condition. This is a theorem. In other words, we have to prove that this one, if we know that this is a strictly sensor stationary, and if it is a strictly sensor stationary, we have to, or if we know this one, we have to prove that any other statistic is invariant with the time delay. So the first side of the theorem is that if this random process is a strictly sensor stationary, the distribution of these pair, I take two samples, okay, and these two samples at time t and omega over 2 pi becomes A and B. So this distribution should be same as the distribution at any other time delayed version of these two. So if I take x at time t and x at time t plus pi over 2 omega, the distribution of these guys should be same. So if I time delay both samples, distribution should remain invariant. In that case, it is sensor stationary. So if we do that, these two pair, x of t becomes this one, and x of t plus pi over 2 omega will be changed. So in other words, you could write. So what you could see is that this vector is related. So x of t, if I write it in a x of t and x of t plus pi over 2 omega becomes equal to related to A and B, and a matrix which is just a rotation matrix, and this rotation is a rotation with the angle of omega t. So that means that if you take the random pair with coordinates of A and B, okay, and if you rotate it at the angle of omega t, this point will have x coordinate will become x of t, and y coordinate will become x of t plus 2 omega. So in other words, now this rotation is the angle of rotation is omega t. So because if my distribution is circularly symmetrical, this rotation will not change the distribution. So this distribution, based on what we have learned in previous chapters, distribution of this guy and distribution of this guy is same, and vice versa. So therefore, AB must, the PDF of AB must be identical with the distribution of its rotated value, which is this one, for all rotations. So if we have the strictly sensor stationary, distribution of that is equal to that. And therefore, this distribution is circularly symmetrical, because if we know that the distribution is not changing with the rotation, it means that it's symmetrical. Now, if it is symmetrical, distribution is not changing. So it's kind of like, but this is a first order statistic. Second order statistic is also trivial. Conversely, if the joint PDF of A and B is circularly symmetrical, you could show that the joint PDF of any arbitrary samples is equal to this one. So this is very easy to do. I will leave these to you as exercise. As a conclusion, a narrowband signal of this form, in phase and quadrature, is strictly sense stationary if the pair of in phase and quadrature components are circularly symmetrical. Moreover, if you say that in phase and quadrature components are independent, then they have to be normal. In other words, a narrowband random process, if it is normal and wide sense stationary, these two guys are having same variance. Uncorrelated mean is